Hello, everybody. We have one last topic that we have to talk about when it comes to interpolation, and this one's going to take a little bit of a different approach. Um, with that, we're going to need some new tools to be able to solve things in terms of MATLAB. So we have two different videos that's going to round out this section of the notes. One of them is on this next topic, which is called Cubic Splines, um, and then one that has to do a little bit with code, but that one should be really, really short. So why don't we jump into it and we'll see what we have to see. So as I said, splines, cubic splines here in particular, but in the for you to try, there's actually a question that gets you to practice using a different kind of splines called quadratic splines. It's just that cubic ones are the ones that are commonly used. So let's talk about why. Why would we use a different approach? We talked already about how with some of the Lagrange interpolation method, one problem is that when you get a lot of data, you get a high degree polynomial that oftentimes might oscillate and not really reflect the nature of the data that's there. Cubic splines kind of avoids this entirely by ensuring that what you get, no matter how many points you have, is never any higher in degree than a cubic. And you wonder, why is that? How can you have like 10 points and yet have only a cubic that goes through them? And the answer is, well, you don't. The idea is that you're going to have multiple cubics, and they're going to connect each piece in a particular way, kind of connecting the dots using a series of different cubics. So you get something that is not just one polynomial, but instead is a piecewise function. It's a piecewise cubic function that is specifically chosen to take into account information at each data point. Like perhaps the heights of the points. You'd want the cubics to go through the right points in order to make sure that you're connecting the dots properly. But there are lots of different cubics that could join 2 points. So there are other conditions that you have to put in into place as well that goes along with that. And we're going to see that comes out in a few different choices that we can make. So this method, this piecewise function method, is called splining, and it presents the advantages that, well, you avoid the swings that are characteristic of higher degree polynomials, and cubics have the flexibility, enough flexibility, so that you can choose them to have a particular height, derivative, and even second derivative at different data points. As I said, there are going to be a couple of choices we can make in here, and so we're going to see that come out as we get into our first example. And if I were to ask you in a test situation, I would have to give you a pretty clear set of instructions on how to construct one of these splines. So as I said, different kinds of splines can be created. We're going to demonstrate the concept in an example as for a single version of this. So here's the example. Construct a cubic spline that interpolates these 3 points. So we have 1, 0, 3, 8, and 6, 5. So if I were to draw this out, here are the 3 points that we're connecting. So 1, 0 looks like it's right about there. 3, 8 would be 2, 3, and like way up here somewhere. And then 6, 5 would be 4, 5, 6, and like up here somewhere. Okay, so the idea is I need a cubic that joins these two. Maybe that cubic looks like, oh, I don't know, this. I need a cubic that joins these two. Maybe it looks like that. Here's the thing, though. When you're creating a cubic spline, you can actually insert a couple of extra conditions, and we're going to see why, that ensures that the way they connect is smoothly done. So, right, the one that I just drew might be a couple of cubics that do the trick. But we might be able to find cubics that, well, come up and have like maybe that's coming close to a point of inflection or something here. And then this other cubic on the other side might latch in and have the same derivative here, even second derivative, to make sure that the change is smooth. And see, like that way, maybe I can connect using 2 cubics that have just the right properties that make this a really smoothly transitioning function. That's the beauty of this whole thing. So we have 2 different cubics. I don't know if this is what it's going to look like. Maybe it looks something like this, but we're going to have the first cubic being this one, S1. The second cubic being this one, S2. And our job is going to be to figure out what the forms of S1 and S2 should be. So the first one, between x equals 1 and x equals 3. So if I draw these out, this is 1, 3, and 6. We're going to assign a general form of this. It's a little bit arbitrary what I'm centering it around, but I'm going to center these pieces around the left endpoints of each. So you can see that I'm building a polynomial around powers of x minus 1. So x minus 1's here, x minus 1 squared is there, x minus 1 cubed is there, and you can see 4 coefficients, a1, b1, c1, and d1. So this function is a cubic function. It's going to be completely defined by whatever those coefficients are, and our job is going to be to figure out what those should be. But interesting, right? Because we only have 2 points of information. You know, maybe there's some work to be done. The second piece we're going to do similarly with a different powers of x minus 3. As you can see, x minus 3 squared, x minus 3 cubed, and coefficients of a2, b2, c2, and d2 is the way that I have kind of put this together. So you can see, right, that we have 8 different coefficients that we need to solve. And our job is to find what they are, because that's going to define things. So our job is going to be to find the coefficients in each of these cubics. There are 8 of them in total. So we need 8 different conditions to solve for them uniquely. Okay, so that's a big order. We can do it though. Let's check this out. Okay, starting off, we have some information that we know right off the bat. I know that I want the first one, this first one, to have a height of 0 at the left endpoint and a height of 8 at the right endpoint, because they go through 1, 0 and 3, 8. So I need those 2 things to be true. So those are 2 conditions that I'm imposing on that first cubic function. There are 2 more conditions that I can impose on the second cubic function. The second one has to go through 3, 8 and 6, 5. So at the left endpoint, S2 of 3 had better be 8. S2 of 6 had better be 5. So that's 1, 2, 3, 4 conditions. We've nailed down 4 conditions right from the start to make sure that the height of the spline, the heights of the spline, I guess, are correct at each point. 2 for each piece, and you can see that pretty easily. That leaves 4 conditions to try and find the 4 other coefficients. And those are going to be chosen to make sure that this spline is as smooth as possible. So 2 of the conditions are to make sure that the first and second derivatives of each piece at the connecting point match. So I need to make sure that S1 prime at 3 is equal to S2 prime at 3. I need to make sure that S1 double prime at 3 is equal to S2 double prime at 3. So let's write those down right now. So S1 prime at 3 has to equal S1 or S2 prime at 3, and S1 double prime at 3 has to equal S2 double prime at 3. That is not an N, that is a double prime. Okay. So, and actually, why don't I just write these down up here? We need S1 of 1 to equal, I think it was 0 in height, that's right. S1 of 1 has to equal 0. S1 of 3 has to equal 8. S2 of 3 has to equal 8, so they have to be the same height at the middle. So it connects, and then S2 at the right endpoint should be a height of 5. So S2 of 6 is equal to 5. So we've got these 4 conditions right here that we're using to help to nail things down. We have these 2 conditions right here, which are going to nail down 2 more coefficients. So we have 6 conditions in total right now, but we still are missing 2 that we would need in general to be able to solve for all these coefficients uniquely. So the remaining two conditions, it depends on the type of spline we're seeking. These typically regard the behavior of the spline at the start and the end points. So, i.e., for this example, at x equals 1 and x equals 6. Okay, there are a couple of options here, but they're not the only ones. There are lots of things you could foreseeably do as different choices for a spline for some reason. So one common choice is a natural spline. A natural spline sets the second derivative to 0 at each of x0 and x2, each of the endpoints. So i.e., that would set s1 double prime at 1 equal to 0, and s2 double prime at the right endpoint would equal 0. So that's essentially saying that you want this curve to end such that, well, you know, it's kind of going to look like a point of inflection. So like whatever the cubic looks like, maybe it comes to a stop right where it would look like it was about to come into a point of inflection or something like that. I don't know exactly how to draw that, but it would come to a right there, right? Like if I was about to continue this, maybe it would look like that, but I'm saying that this endpoint ends with that second derivative equal to 0. Okay? And maybe it ends on this side like this. Who knows? Okay? So second derivatives equal to 0. That's one of the options. Okay. That's not the only option. Another option that's pretty common, especially if you're trying to fit a spline to another curve or do something like that, is to so-called clamp it. Okay? So a clamped spline kind of imposes the first derivative at those endpoints, those same endpoints, is set equal to a particular value. So maybe I know based on the property of the function that I want for the derivative at one endpoint to be 2, and at the other endpoint I want it to be 4 or something like that. I can use that, and like as I said, if you're trying to basically interpolate another function at a few endpoints, maybe you know something about that function. Maybe you know what its derivative is, and you can clamp the spline so that it hugs that curve as well as possible. So a few different things. So you could have s1 prime equaling something at the one endpoint, and s2 double prime, or s2 single prime at the right endpoint being equal to something else. Okay, for this example, we're going to use a natural spline. Oops. And so that's going to make sure that s1 double prime at 1 and s2 double prime at 6 are both set equal to 0. So those are going to be our 8 conditions in total. Let's go through them one more time. I need to make sure that the heights are good for each of the pieces. So the left piece has to have the height at each of the endpoints of that piece equal to the correct height. The second piece has to have the heights equal to the right thing. So that's 4 different conditions, 2 for the left, 2 for the right. 2 conditions are set to make sure that the connecting piece, the connecting node between the 2 pieces, matches in its first and second derivative. That's our 5th and 6th conditions. And then the last 2 pieces for a natural spline are going to set the outer nodes such that their second derivatives are equal to 0 there. So all of these conditions will allow us to set up a G system of equations. What's supposed to go there? Let's say gigantic. I'm not sure that's what it was supposed to be, but it is solvable. It's just going to be gigantic. I'll go with that word right now. Okay, so let's actually play this out and see how this looks. If I start to work with these 4 things, we can see that these are the 4 conditions that I laid out. I need S1 to have a height of 0. I need S1 of 3 to have a height of 8 because I want it to pass through these 2 points. I want S2 of 3 to be equal to 8 as well. And I want S2 of 6 to be equal to 5. All right, subbed it in here just to bring it forward to remind ourselves of what this looks like. This is just me subbing in the 1 into the x, into the x, into the x. And you can see pretty easily that if I sub in this first one, well, 1 minus 1 is 0, 1 minus 1 is 0, 1 minus... This makes it pretty clear that a1 equals 0. And right off the top, I know that one of those coefficients must be 0. So then if a1 is equal to 0, this one is gone because this is equal to 0 right there. And in the second one, if we sub in 3 now, we're going to get 3 minus 1. 3 minus 1 squared, 3 minus 1 cubed. I need to make sure that this is equal to 8. And if I simplify this down a little bit, we get 2b1 plus, okay, let's be careful here, 2 squared c1, that's going to be 4c1. And then a 2 cubed d1, so plus 8d1. That has to sum to 8. All right, our job again is to find those coefficients. We've got a1 so far, but we've got a lot of equations to go, so you can see where this is going, right? The next condition says that the second spline has to have a height of 8 when I sub in x equals 3. And so I've subbed in 3, 3, 3. Those are all 0, so you can see why it's very useful to have a form that involves a center point with those nodal values. But in any case, we get pretty simply a2 equals 8 here. And finally, the right endpoint of the second piece has to have a height of 5 when I sub in a 6. So that means I'm subbing in 6, I'm subbing in 6, I'm subbing in 6. I know that a2 is equal to 8 from what we just did on the last line. So it looks like this is going to give us, quite a mess here, quite a mess. So let's do this. b2 times 3, I'm going to bring this 8 to the other side in the end. So this is going to be 3b2. I get 3 squared c2, so 3 squared is 9, so plus 9 c2. And then 3 cubed d2, 3 cubed is 27, not 9. So I get plus 27 d2 is equal to 5 minus the 8 from before, that's negative 3. All right. So this is what we've got. I've used what I know about a1 and a2 here to try and make things a little bit better. So we've got 2 coefficients we know and 2 equations here that involve other coefficients that are going to be involved in some system that we have to solve. Okay. Our other conditions deal with derivatives. So we should find the derivatives of each piece. Okay, so let's do that. S1 prime of x. S1, let's remind ourselves of what S1 looked like. S1 of x was equal to, it was a1, although we know that a1's 0 now, but I'll just keep that there for now. It's a1 plus b1 x minus 1 plus c1 x minus 1 squared plus d1 x minus 1 cubed. So you see, it's not actually hard to find the derivatives because, well, it's just a polynomial. We're going to get here a b1 plus 2c1 x minus 1 plus 3d1 x minus 1 squared, like this. Similarly, from before, S2 of x was equal to a2 plus b2 x minus 3 plus c2 x minus 3 squared plus d2 x minus 3 cubed. So if I take the derivative of that, well, we're going to get, okay, the a2 again. We already know what it is, but the derivative is gone anyway. So we get a b2x goes down to a b2. We get a 2c2 x minus 3 and a 3d2 x minus 3 squared. Okay, so I can see what those derivatives are, s1 prime of x and s2 prime of x, and our fifth condition said that those derivatives have to match at the middle node. So I need s1 prime of 3 to specifically be the same as s2 prime at 3. So the two should be equal. So let's see what that gives us. S1 prime of 3 is going to be b1 plus 2c1 3 minus 1 plus 3d1, 3 minus 1 squared, and this has to equal s2 prime at 3. And that's going to be b2 plus 2c2, 3 minus 3. I'm doing this just to demonstrate where this comes from, because otherwise it's going to disappear. I'm just making these two things match when I substitute in x equals 3. So hopefully that makes some sense. But what's nice is that, okay, this is again dead. This is again dead. And I can kind of organize things now. Do I know any of the information? I think I know just A1 and A2 at this point. So I guess we just have to kind of maneuver things around here. I think we get B1 plus 2 times 2c1 is 4c1. I have 2 squared times 3 is 12d1. I'm going to take this b2 to the other side and say minus b2. That is to equal 0. So this is going to relate a bunch of variables as well. And that's going to be added to the system of equations that we have to solve. Okay, we're getting there. We've done the first 4 conditions. We've done a 5th condition for the first derivative at the middle node. And the next one that's going to come is the... Oh, interesting. Yeah. Oh, the last conditions are placed in the second derivative. Yep, so we need to calculate those conditions as well for the second derivative. So if I take the second derivative now, s1 double prime at x is equal to... All right, let's go up and do one more derivative here. There's a lot to keep track of with this, right? No single step of splining is terribly hard, and they make a lot of sense when you know what's going on. But there are a lot of things to keep track of, especially when you're trying to do this for the first time in a year, which is where I am, right? I remember teaching this stuff about a year ago, but it's not like I've been splining in my spare time since then, so I have to remember how this goes as we present this material. So there's the second derivative of s1 double prime, and I need the second derivative for s2 double prime as well, and that's going to be, let's see, 2c2 plus 6d2. So 2c2 plus 6d2 times x minus 3. I do believe. Okay, so those second derivatives have to match as well at the middle node to get that 6th condition. So that means that I need s1 double prime at 3 to equal s2 double prime at 3, and that yields 2c1 plus 6d1, 3 minus 1, is equal to 2c2 plus 6d2, 3 minus 3. This is gone. And if I kind of simplify, maneuver this around, so we have a nice equation. We get 2c1 plus 12d1 minus 2c2 is equal to 0. And there is yet another condition. All right, so that's how far we've got so far. We've gone through 6 different conditions. The last thing we need is to take into account what kind of spline it is, and as indicated, I think a couple pages ago, we're looking for a natural spline here. So a natural spline, on a test, look for that keyword, whether I want it clamped with a particular derivative imposed at different spots, or if I'm looking for one of these natural splines where I put the endpoints with a second derivative equal to 0. That's what we have here, this and this. Okay, we just calculated what the second derivative is, so this isn't going to be hard. We're going to get s1 double prime of 1 equals 2c1 plus 6d1, 1 minus 1. I need this to equal 0. And hey, 1 minus 1, that's 0, so this goes away. And it looks like we've got another one of our coefficients, actually. c1 must be 0 for this to be true. That's neat. We could go back and we could, sub that into some of what we had before, because I think we had a couple of other conditions that depend on this. So we could sub this in to some of our other equations. To reduce them down. That's going to be important. Okay. And the other thing we need is for S2 double prime at 6. That's going to equal, let's see here, S2 double prime at 6 is going to be 2C2, oops, that's not a 3, 2C2 plus 6D2, 6 minus 3, that has to equal 0 as well. And that's going to bubble down to be nothing more than a 2C2 plus, and then what do we have? 3 times 6D2, that's 18D2, that is equal 0. This is another equation that we have. So we've solved for 3 coefficients. If you go back, we have 5 other equations with 5 unknowns. And so, between all of that, we have enough that we're going to be able to put down those others as a system of equations, and our job will be to solve them. So check this out. We have those equations all, so this is after subbing in that C1, and I'll let you verify this as for you to try. Although really, you could honestly play this game with any kinds of points. You could pick 3 points of your own and play like a little splining game, because I know that's what I like to do with my Saturday afternoons. But honestly, it's not that hard to create these. It's just a matter of remembering what steps are involved in this. So we have 5 equations, 5 unknowns in B1, D1, B2, C2, and D2. Okay, well, you can use like a high schooly approach and have like a bunch of equations and solve for some and substitute them into others and so on and so forth. And that's a really not great idea. Here's the reason why. It's hard enough to do that when you have 3 equations and 3 unknowns. Here we have 5 equations and 5 unknowns in general. That is going to be your best case scenario. So the best thing you can do is to use Gaussian elimination and matrices. Okay, as I said, you can do it without, but it might be very ugly. Would not recommend. But in that form of using matrices, the idea is, can you solve this system of equations that looks like this for these 5 variables? Okay, so that's a pretty tedious amount of work. And no normal person would take a system of 5 equations and 5 unknowns and start to work it out by hand if it's going to take them 20 minutes to do so and potentially cause you to run into errors and stuff like that. But basically, if you solve this system, however you prefer, whether you do it by hand or whether you do it with a computer, or you use an online calculator, or angels from above come down and give you the answer, which wouldn't it be nice if that happened? But unfortunately, it doesn't usually. You should end up with these answers right here. Right? I could work it out by hand for you, but then it would double the length of this lecture, and I don't think it adds anything, right? You can pair those with what you found before, which were those 3 values for A1, A2, and C1. And with those, that will define our piecewise function. The A1 and the C1 are 0, so you can notice we only get an x term and an x cubed term for that first piece. And for the second one, you can see the coefficients come out right here, right? There's A2, 8. The 2 is B2, right there. Minus 3 halves, this one right there. And D2 equaling 1/6, right there. If you were to go and graph this, right, you only want to use the first piece of that spline on the first interval, and you want to use the second piece for the second interval. Of course, I've said less than or equal to 3 for the first one and less than for the second one, so they don't overlap, but it doesn't matter what you choose because they're the same height at 3, so it doesn't make a difference. Okay. Yeah, I want to stop right there actually and just bring it in for a little bit. As you can see, it's a pretty long and involved sort of problem. I hope it makes kind of sense. So what we're doing is just trying to find coefficients, 2 cubics that could be used to pass through sets of 2 points in such a way that they have similar properties at that middle node. You could extend this, of course, to have, say, 3 cubics spanning 4 different points. And in general, you could do this for as many points as you want. This is a useful technique when it comes to things like computer graphics. It's pretty widely used. It's an important technique to know. I stopped there because really how I would solve that system and how I would expect you to solve that system is not to spend 20 minutes or 25 minutes solving that matrix equation by hand. I think that at this point, it's a little bit wasteful of time, especially if you have, right, if it was a 2x2 system or even a 3x3 system, cool. 5x5 though, we have tools for this. MATLAB is exceptionally good when it comes to linear algebra, and so I'm going to piggyback off this video with another one that explains how to use matrices in MATLAB. And I want to make it clear that on a test, if I wanted you to actually solve a matrix like that, I would want you to use software or a calculator or MATLAB in order to do so, okay? So in that, I want you to become really comfortable. So we're going to do a short little video following up with this one that explains kind of what MATLAB can do in terms of vectors and matrices. So hopefully you're willing to join me. There's a lot to learn still. I hope that even though it's a little bit of a slog, you'll agree with me that there is no particular step, right? We're taking derivatives of polynomials. That's not a hard thing to do. So I don't think that this technique is all that tough, but there are so many steps and it's really just understanding why those steps make some sense. So let's stop there for now. I hope you'll join me with that next video on vectors and matrices in MATLAB, and that will round out this section on interpolation and stuff. So I hope it's been good. I hope you've understood, and I hope that you'll contact me in case you need any help. So until next time, I bid you all a fond farewell. Take care of yourselves, take care of each other, and bye for now.